thank you all for coming to this talk. For my talk today, again, for those who I've met before, my name is Andrew Case. I'm the Director of Research at Volatility. And what we like to do, if you saw the demo at lunch, we like to do a lot of memory forensics work. We like to do research into the latest threats and techniques we're seeing in the wild. And so something that we do quite often is if we see a recurring pattern where attacks that we think are interesting or we see other vendors publish about it, once we see where there's enough of a pattern, a certain part of Windows, a certain part of the operating system's getting attacked with enough frequency that is interesting to us, we do these big research deep dives as a team. So if you've seen our talks, which I know a couple people in the room have, if you've seen our talks over the last year or two, we did a big research deep dive on all of the rootkit techniques that still work on Windows 10. We just wrapped up one recently on all of the credential access techniques that work on Windows 10 and 11 and that get used in attacks. And our latest one, which I'll be talking about today, are the ways that malware evades EDRs. Because what we saw initially was in those really targeted attacks, espionage-based attacks, really sophisticated threat groups, we would see where the first thing malware did was evade the EDRs on the system so that they could roam undetected. And when it's just in that space, when it's just like us and other companies that are really working in that targeted space, it usually doesn't make sense to do a deep dive because the vast majority of people aren't going to see it. But then what we noticed is really any ransomware that was being deployed, not even from the best groups, any ransomware, any malware in the wild at all, the first thing it did was bypass the EDRs. So then if attackers want to move laterally, if they want to actually infect files on the system, if they want to gather credentials and so on, the EDR is completely blind. The EDR is still there and running, but it's not actually doing anything. And we would see this, it's kind of the second bullet point in the slide, but it's very often where we were doing memory forensics, we're loading it into Volcano or Volatility, and right next to the malware that's popping out in our analysis is the EDR. The service is still running, the processes of the EDR are still active, but it's not actually detecting anything, and the malware is able to do whatever it wants. So what we wanted to do and what we did, and it was some very fun technical research, is we broke down every technique that was ever seen in the wild or in our own investigations on how malware was bypassing EDRs. How on these systems where EDRs were configured by the customer, running correctly, set up how they were supposed to be, but the malware could do whatever it wanted anyway. And when we do these research projects as a group, we want our end results to hit a couple goals. And again, if you've seen some of our other talks, this is the same slide that's always there. We want effective techniques, so we don't want a million false positives. We don't want the auto analysis to take days or hours or weeks. So we want it effective, very few to zero false positives, and we want it as scalable as possible. When we do these projects, we have a very large data set of memory samples that we can use, that we have access to. Some of them are clean, some of them have third-party software, some of them have malware. And we run all these techniques that we come up with over that data set to make sure that we're actually meeting these goals. And you'll see with some of the new Volatility 3 plugins that were developed as part of this, we were able to meet that goal for every evasion technique in the wild. So just a quick recap. This is the ways that EDRs monitor system activity. So one of them, going back to available since XP, was kernel callbacks. So this made it into the art of memory forensics and was very early Volatility plugin. So the idea is inside of kernel memory in your kernel driver, you can register for callbacks for a bunch of different activity. And related to this talk, there's really two of them. One is when a process is created, your kernel driver can get notified to say, hey, the process from this path as this user and so on is being created. That lets the EDR scan it or decide if it's a malicious process or not. Same thing if a DLL is being loaded into an already running process. Two of the newer ones are event tracing for Windows, normally called ETW. This is somewhat similar to what was talked about this morning with the Apple tracing framework, where you can get notified of really dozens and dozens, a quite wide range of system activity in your software. And so you can register this on the more modern versions of Windows, and a lot of EDRs rely on this for their visibility. The third one, AMSI, the anti-malware scanning interface, this is where previously, things like PowerShell, macros, VB scripts, JScript, all of these scripting-based languages, things that aren't like an exe or a DLL file, there was not a great way to scan those or for EDRs in real time to know that those were running. So Microsoft came up with the AMSI interface so that before your PowerShell script runs or your macro gets to kick off, whichever of your EDRs or AVs have registered for that interface, they get to scan them. So that's how Defender really started to kill off PowerShell being so easy to use, and that led to what was like dozens of talks around the industry on all the AMSI bypasses. And then the last one, which is what we're really going to focus on today, is the system call monitoring. So this is where your EDRs will hook the lowest level system call implementations so that right before your process calls into the kernel, it's able to see what you're doing, and we'll have some pictures of that here in a second. Now, as you might suspect, and I kind of hinted towards it, all of these are bypassed. You can have all the EDR on the market, and the first thing malware does is set up everything so that the EDR doesn't see any of the malicious activity. And if you've never seen one of my talks before, I have these numbers after certain parts of it. The very last slides are all the references. I think this talk has like 60 references. Like I said, this is a big project, lots of reading. So if you want to go back, you have all of that available. But malware essentially can bypass all these techniques. We have some blogs on the Volatility blog, on the Volatility blog for doing this. But the takeaway is all these places that Windows has provided for EDRs and AVs to monitor, the malware has bypassed all of them. But what was interesting to us from a research standpoint is if you took the kernel callback bypasses, the ETW bypasses, the AMSI bypasses, there's volatility stuff you can run right now and detect those. Those are what I would rate as trivial to detect with memory forensics, where you can see with the system call monitoring, like I said, the code that monitors at that low-level interface before you switch to the kernel. Before the work we did for this project, there was nothing out of the box for memory forensics that you could use to detect it. So if you had malware using this bypass technique, which basically every ransomware sample out there does that now, you could not detect that right away with volatility. So if you wanted to do it at scale, if you weren't, you really had to be like beyond an expert, like coding level, source code level with volatility to make it work. So we wanted to research it so that we would have these automated plugins. So some quick recap for people who forgot their operating systems class. When we're talking about system calls, there's two pictures here that are going to help set it up. The first one on the left is, this is the picture in one of the early pages of Windows Internals, the book series. And what you have is it's showing what is in user land or user mode. So user land, user mode is where processes live. That's where your application executable runs. That's where your DLLs are, and so on. And then you have this well-defined boundary to transition to kernel mode, which is where the operating system and the hardware and the drivers are. And the main takeaway here, the thing to understand, is processes are very limited in what they can do without making a system call. They can read their own memory, they can write to their own memory, and that's really about it. If they want to interact with the file system, if they want to manipulate the registry, if they want to send data on the network, receive data from across the internet, and so on, they have to ask the operating system to do that for them. So they have to cross this kernel boundary and ask the operating system to go fetch data off the hard drive or go fetch the data off the network card so that something like your browser can actually deal with it. And this is why EDRs are so interested in this interface, because when they hook at this lowest level possible, they can see all the activity. They'll see every file the malware interacts with, every other process it tries to interact with, if it tries to use the registry for persistence, and so on. By hooking at the system call level, you can accomplish all of those goals. And then what we have on the right here with the arrow coming from that boundary, this is from sysinternals. So on a running machine, you can have sysinternals generate the set of calls that are made when you make a system call. We're going to start at the bottom. So you can see at the bottom here, MS Edge. So this is the browser process. It's eventually going to move its way closer to the kernel. If you look at line where it starts with 11, we are now in NTDLL. So NTDLL is what's actually implementing the system calls. This is what's going to transition us from that process into the kernel. And as we'll see on the next slide, this is exactly where EDRs hook. So in this case, the system call in question is ZW create file. So if the browser, again, is going to create a file or read a file, write to a file, it's going to go through this interface. So by hooking that function, you can see all of that activity dynamically. The EDR can log it, it can stop the operation, it can do what it wants. It has full control on that transition into the kernel. And then again, if you look at line 9, where the lines become prefixed with K, that's the boundary. Now these are the kernel handlers for those functions. And again, we want to inspect where that boundary is to see if EDRs have hooked it, because this is the main place our bypasses are going to operate. So what we have here is looking at the system call handlers. If you're not a reversing person, this is the only IDA Pro screenshot, but I always manage to work in one into every talk. But it's really critical here. What you're seeing on the left is this is the implementation inside of NTDLL for one of the hundreds of system calls. So in this case, it's NT protect virtual memory. This is one of the functions malware will use so that it can inject code and have shell code and so on. And there's three things to take away from this picture to try to remember throughout the talk. To make a system call, you have to do three things. You have to update the R10 register, so that's going to be one of the parameters. Importantly, you also have to update the EAX register with the system call number. In this case, you can see it's 50 hex. So what that means is for this version of Windows, that is the index for protect virtual memory in the kernel. Within that operating system space, within the kernel, is a table for all the system calls, and they get indexed by a particular number. And so in this case, the operating system knows, or this NTDLL knows, that index 50 hex into that table is protect virtual memory. And then if you look more towards the bottom, depending on how new or not your hardware is, you either make the syscall instruction or int2e. But this is where in NTDLL, for every system call, we are actually transitioning into the kernel. And the reason we're focusing on this so much is because if you look at the picture on the right, that is the same exact function after it's been hooked by an EDR. So what the EDR is going to do is it's going to overwrite the entire implementation so that instead of transitioning from normal Windows code into the kernel, you first have to pass through the EDR. And again, this protect virtual memory is a prerequisite step in many types of code injection and so on. So the EDR can say, hey, why are you trying to change the memory of LSAS or some other target, other process that I'm targeting, and it can just stop you. Your EDR can say, hey, I'm not going to allow you to do that. You can't do it at that point unless you have some other workaround. And so your malware is going to be stopped in its track. So with that background, we want to look at some of the bypass techniques. Like I said, we studied every single bypass technique we could find references to from our own work, from online, and so on. And the first one is the first bypass technique is very closely related to the last slide. So this goes by a bunch of names, module unhooking, system call unhooking, API unhooking. It's all exactly the same thing. The basic idea is malware is running on a machine. It's running in a process that either it started or it injected code into, and it wants to make system calls without EDRs getting in the way. So what it's going to do is unhook that system call. It's essentially going to take that hooked implementation that the EDR has hooked and revert it back to the original one. So I have a picture here from what was a really nice article. This was like from earlier this year, February, March timeframe, but all the malware does the same exact thing. So in the block here, what it's saying is the malware wants to unhook all the system calls, so it can make all the system calls that it wants without being interfered with. So what it's going to do is get a clean copy of NTDLL. Remember, that's where the code is for all of the original system call implementations as they are on disk. It's then going to find the code, so where those instructions are, and it's just going to overwrite all the hooks that the EDR placed. So the EDR made all the effort of hooking what's probably going to be 100 plus system calls in memory, and in a few operations, the malware is going to make it where the EDR is not present in that process at all. So now you have the clean NTDLL from disk running in this process as memory. The malware can do whatever it wants and make all the system calls, and your EDR is totally blind. Thankfully, from a memory forensics perspective, like most things, we don't have those problems. So we're able to not only detect the fact that this has been unhooked, so that this type of tampering has taken place, we can also point directly to the process that has been unhooked, as well as the functions that have been unhooked, which if you have a bunch of memory samples, this points you right to the malware. So the basic idea behind this detection is, if you think about it, if you're on a system like a production enterprise system where an EDR is active every process is going to have its system calls hooked. And like I said, in most cases, it's going to be like 100 plus system calls. So then when you have malware come to that machine, it's going to pick on maybe 1 or 2 processes at most that it's targeting, and it's going to unhook those. So in that case, let's say we have 100 processes, malware unhooks 1. We have 99 that are still hooked by the EDR, and 1 that's been unhooked. So what we did is we wrote a plugin that compares them. We just compare the implementation across all the processes, and we can say, hey, this one strange process has its own implementation where the 99 other ones have the same. We like to make research. We like to set up our experiments so that we're not dependent on a certain commercial product that might change. We also like to make experiments that other people can replicate, and we're obviously fans of open source, right? So to set this up, if you want to test this on your own, there is a really cool project called Silent Strike on GitHub. It is an open source EDR meant for bypass testing. So the whole point of it is it'll hook whichever processes you tell it to spawn. You can try all your bypass techniques and then see if your EDR still catches it or not. And if you Google Silent Strike, there were some really cool projects. People took like all the major commercial EDRs, tested the bypasses and so on, and Silent Strike allowed that to happen, and we basically reused it. How Silent Strike works is it hooks NT protect virtual memory, the same function that we saw before on the slide with the disassembly. So with Silent Strike, it's not meant to hook all the processes. Remember, this is not an enterprise EDR, it's meant for security testing. So you start specific processes under Silent Strike, and then it will hook NT protect virtual memory as any commercial EDR would. So we took a base Windows 10 install with no EDR. We then spawned off a Notepad process and a WordPad process under Silent Strike. So now you have these 2 processes who are hooked as if a real EDR would be hooked, and then we took a memory sample. We then used R77, which is another open source project on GitHub, for doing this type of module unhooking. We then unhooked Notepad and took a second memory sample. So the first memory sample has 2 processes that are quote unquote protected by Silent Strike. We then used R77 to revert one back to the original one, which is exactly like malware does. And then this is that new plugin I mentioned. It's called Windows.unhook system calls. And the idea is this is where we're comparing the implementations. I cut the slides because we check, I don't know, 50, 60, 70, 80 system calls, something like that. But you get the point from what we see here. The first set of output is from the memory sample where we launched Silent Strike with Notepad and WordPad running. And you can see it's saying for the plugin saying for NT Protect Virtual Memory, those 2 processes have distinct implementations because all the other ones have the original. And then if you look at NT Open Process, Query Virtual Memory, and so on, there's no processes with distinct implementations because they just have the original one as it was running. So this is what we would expect. Those 2 processes are protected by Silent Strike because it's hooking NT Protect Virtual Memory. We then have the second memory sample, like I said, where R77 was used to unhook Notepad. And if you notice, Notepad's not in the distinct list anymore because its implementation has been reverted back to the original. So we tested this with the open source one. We then ran it on some real memory samples we have with actual like EDR bypassing malware. It's the same exact thing. If you see a process listed here, 1, it's bad, and 2nd, it's the malware. And so out of your total data set, it tells you exactly which functions are unhooked and in which processes they're unhooked. So the next thing we wanted to look at were suspended and cloned processes. The idea here is for the previous technique to work, the unhooking, kind of V1 of that, what malware was doing originally, was just going to disk and reading NTDLL. They need a clean copy of all of those system calls. They're going to want to overwrite the original implementations, so why not just go read it from disk? So then what happened, and it kind of makes sense, is some EDRs are like, it's pretty weird that random processes are opening handles to NTDLL on disk, reading in all of that into memory. Like, why does a normal process need to read the raw code of NTDLL? That doesn't make a whole lot of sense. So some EDRs are like, hey, you're reading NTDLL. At a minimum, that's suspicious. Worst case, you're malware trying to do unhooking. We're just going to stop it before you can even get access to those bytes. So this was actually super nice from a detection perspective. If you've dealt with process hollowing before, you know that the first prerequisite step is making a suspended process. And what the malware authors did here was basically reuse that idea to get access to a clean NTDLL. So the background here is on Windows, you have a create process API. You can probably figure out that that's used to create a new process. By default, if you call it with just the flags by default, that's going to create the new process, it's going to run, it's going to spawn, it can do its own thing. But there's a special flag that you can set called create suspended that makes what's kind of like a half-baked process. So what this means is, in the malware case, it's going to spawn off some other process. It's going to call create process with the create suspended flag. What Windows is going to do is make kind of like a half-made process. So it's going to set up an address space for that new process. It's going to have a process ID and so on. But the only executables it's going to map are whatever exe you're running and NTDLL. And then after that, it's going to return control back to the parent process, which is the malware in this case. So what you have in memory is a half-made process. Because that process isn't fully created yet, your EDRs are not notified about it, so your kernel callbacks, your ETW hooks, those have no idea that this kind of half-made process is there, but you have a full-blown address space where NTDLL exists before EDRs even know it's there to hook it. So you have this clean NTDLL in memory. And then because you're the one calling create process, you have a handle to that child that you just sort of half-made. So then, as you could probably guess, the malware uses that handle, reads the clean NTDLL, and overwrites the hook, all without ever having to read NTDLL from disk itself. Now, this is something that annoyed me greatly, because there was a lot of social media about how this bypasses all memory forensics, so I wrote a plugin just to detect it, and then put it on like Twitter and LinkedIn and things, as some of you noticed, because you shared it and so on. Because this is super loud to memory forensics. This is all the gory details, but the basic idea is you have processes in memory. Volatility knows how to find those. Every process has one or more threads associated with it, which we know how to find those. And then inside that thread is a count of how many times that thread has been suspended. And you might suspect that your suspended process has at least a count of 1. So we wrote a plugin that enumerates every process, every thread, and if the thread suspend count is greater than 0, which is the default, we report it. We ran this over our 600 plus something memory samples, and the only processes that were reported, with the exception of this weird like browser process that we figured out how to skip, the only processes that were reported was either EDR bypassing malware that did this, or a bunch of hollow process hollowing techniques that we didn't know we could detect this way before. So it was actually really helpful because now we can detect process hollowing in even more ways than we had before. So in Volatility 3, you have a plugin that does what I just said and prints out any processes that have suspended threads. So this also led us into another interesting part of the research. There was a super interesting project at Black Hat Europe a couple years ago called Dirty Vanity. If you like Windows internals and lots of gory malware details, go read that white paper. It was very well done. The whole point of Dirty Vanity is to bypass EDRs. And the way it did this is it made clone processes. And so the idea was it would have its malware process. It would then clone it. If you're a Unix person, you could think of it as forking the process. So the idea is you have the same process in 2 different address spaces. And it was super interesting because let's say your recipe to get code injected requires you to make 4 system calls. What Dirty Vanity does is it makes the first 2 system calls in the parent. It then clones itself and makes the final 2 calls in the clone process. The end result's the same. There's still code injected and so on. But there was, like I said, the paper was really good. They tested all the EDRs in the market at the time. None of them could catch those calls split across processes. So super interesting work, making the calls across it. But of course, it's super loud to memory forensics like everything else. So we wrote a plugin called Clone Processes. As you would suspect, it picks this up right away. It's also interesting, if you're interested in this, Google the definitive guide to process cloning on Windows. It's like 50 pages of gory API details. But it matches everything that we saw in the plugin. Honestly, if we saw that first, it would have saved a lot of time because we had to do some reversing and things. But that guide is on GitHub, and it explains a lot of what's going on. But the basic idea is when you create a cloned process, you're suspending threads along the way. You're also changing the process state, so Volatility 3 picks that up right away. That's what you're seeing here. So in this case, we are running the suspended threads plugin against a sample infected with dirty vanity. It calls itself fake.exe if you just compile it off GitHub. So we have fake.exe that is being reported, and it has a PID of 6752. So that is us walking, again, the process list, the threads of every process, and if that suspend count is greater than 0, we're reporting it. So this tells us right away that the fake exe PID 652 and then the thread with ID 1964 inside of it has something wrong with it, like this is going to be malware. And then if you look at PS tree, so this is showing the parent-child relationship, you can see what we're picking up on. We ran the original fake.exe. That then clones itself, and that clone has 6752, and then the default, it just launches a little payload that says like hello from dirty vanity. But you can see that we are perfectly picking up on this technique, finding the correct thread and so on, and anything related to suspended processes, clone processes, all of that, Volatility 3 will pick up right away, and that covers a lot of the EDR techniques that we saw. All of the bypasses that I've talked about so far involve overwriting code. So you're going to like overwrite the original implementation of all of NTDLL, or some ransomware will only overwrite the certain functions that they actually want to call, which is a little smarter. But the whole thing's kind of terrifying, right? Because you are overwriting code responsible for system call handling. So imagine if you overwrote that code while that system call was occurring in a thread. Like, that's a very scary thing. You would fail all your computer science classes. So this is really unstable, and EDRs are actually really bad at this, but if you think about it, EDRs could check their own hooks, right? Like if I'm an EDR and I'm monitoring LSAS, and then all of a sudden all my hooks are no longer in LSAS, something's probably tampering with LSAS. So to avoid the instability, there was a few more methods that were developed that were also super interesting. So there's direct system calls, indirect system calls, and then we'll look at exception handlers. The idea with direct system calls are, it's kind of obvious, right? If you remember from the IDA Pro screenshot we had, we saw where R10 and EAX were being set, then we had the syscall instruction. That is very easy to write in code. There is no reason to have to call that original code in NTDLL. Why don't we just do that ourselves? It's like 3 assembly instructions and we're good to go. And then that way, let's stay with NT protect virtual memory because we've seen it a few times. If we just call NT protect virtual memory ourselves, if we make that system call ourselves, then the EDR hooks in NTDLL will never know the difference because we are not going through that code path. Now, this is another place where memory forensics is awesome, because if you read what's very interesting reports about this on live machines, EDRs try to detect this because they'll look at like the call stacks and what a thread's doing and where the call came from. And then if you look at things like Cobalt Strike and some projects on GitHub, they fake the call stacks, they fake where it comes from. It's this cat and mouse game that from a memory forensics perspective, we don't care at all because we can just go find the code somewhere else. So this has a lot of problems for EDRs to try to detect it on the live machine, but like everything else, it's super loud to memory forensics, which is what we like. So the basic idea here is just a warning, there's a ton of gates. So everyone on the Volcano team was aggravated trying to remember all these gates, so heads up on that. So this was the first implementation of direct system calls. It was a project called Dump ERT, but it had a huge limitation because if you notice, this first block is for ZW open process, then ZW close, and this is specific to Windows 7 Service Pack 1. So you would need these definitions for every single system call for every version of Windows out there in the wild. You can't really do that as a malware author. And the key thing here is if you notice for like open process, the move EAX is 23 hex. For closed process, it's C hex. Those numbers change in every build. The string name of the API, so like open process or closed process, those are the same in every versions of Windows, but every build of Windows, the system call numbers are going to be different. So that's why they had to be hard-coded, but obviously this isn't going to work too well. So then we get to all the gates. So the first one was called Hell's Gate, which is a very powerful name for something that's not that interesting in the end. And basically what it did is it made it where instead of having to hard code those specific hex numbers for the system calls, it would dynamically resolve them. So it would get access to the NTDLL on disk, it would walk the PE, find where the export is, and then just parse out the number. Like very basic static analysis. But it was cool, right? Because then on the running machine, as you can kind of see in the code, it just dynamically fills in the number. So if you want to call ZW open process, you have to call what's called the Hell's Gate function with that string. It then fills in the global variable. You then call Hell's Descent, which is like the really over-the-top name for like making a system call. And then it makes the raw system call for you. But this was a big advancement from dump ERT, and you could actually use this in the wild because you could resolve those system call numbers dynamically. But if you notice, you have a syscall instruction and a ret and all of these things in code in the middle of nowhere. It makes no sense that those calls should be occurring outside. And then this is all the rest of the gates, so you have to be thorough when you do talks. So there's Tataris gate, which just puts nops in between the instructions. There's Halos gate, which finds the numbers in a different way. And then I'll skip to the end because it's actually pretty cool. There's a project called SysWhisperers 2. Yes, the 2 means the second one. The first one was not as cool. But SysWhisperers 2 is really interesting. You import the header files into Visual Studio, and then you just call the APIs as if you were in like regular Visual Studio. It looks exactly like your regular C code. You get the syntax highlighting. You can hover for documentation. And in the background, at compile time or build time, it does all of the direct system calls for you. So if you read the source code, it looks just regular like C, C++, Windows programming. But in the background, all your calls at runtime will be direct system calls through dynamic resolution. So there's been, obviously, like a lot of the red teaming tools, real malware, is using this because you don't have to do anything. You just write regular C code. So we want to be able to detect this. As I said, it's very weird to have syscall instruction invocations in the middle of nowhere. And so we took our very large data set of memory samples, and we looked at all the places where legitimate system calls were being hosted, which is all of 3 DLLs out of the hundreds of them that come with Windows. So you have NTDLL, like we talked about. You have WOW64, which is for your 32-bit programs, and then Win32, which is for your GUI system calls. And after testing our very large data set, any syscall instruction invocation outside these 3 DLLs was malware with 100% certainty, because why would you have syscall in like a shellcode block or some other region that's not actual part of Windows? So this is another example of that. Like I said, I'd like to put tons of references in my slides. Thankfully, we don't have to care about this stuff at all in memory forensics, but this actually came out midsummer. It was a super cool malware report, malware called Dodgebox, and I highlighted parts of it in red. It says throughout all 3 phases, the malware does call stack spoofing and a bunch of other things to change where the system calls look like they're coming from. And at the time, which was all of like 3 or 4 months ago, it bypassed every EDR and was able to run freely. So we want to be able to detect this from a memory forensics perspective and not be bypassed like everything else. So what we do is, except for those memory regions hosting the DLLs that we would expect to make the syscall instruction, we have what is pretty flexible automated static analysis to look for within a close enough range where we have all the ingredients we need to dynamically make a system call. Updating EAX or RAX, updating R10, calling syscall or int2e, and then you need to return out of that function somehow. And then, like I said, we ignore all the stupid things, the not interesting things like Tataris gate where they put no ops, and our static analysis doesn't get fooled by that. And so the end result is this is running the direct system calls plugin against a memory sample with Hell's Gate. As you can see, we very directly find the syscall invocation, gives you the process name, the PID, and then the exact address range in that process where the instructions are. Like I said, we tested this against hundreds of memory samples, 0 false positives, only where this type of technique was being used. So then there is a variant of direct system calls. This is indirect system calls. And the idea is, remember, EDRs were trying to make an effort to say, hey, why are you making a syscall instruction outside of NTDLL? So then the malware authors came up with something that was actually pretty cool. So what they did is instead of making the syscall instruction invocation from their shellcode block or their random DLL they injected into memory, they would scan inside of NTDLL for a syscall instruction. So then what they do is they update the registers as needed, and then they jump to that syscall instruction. So that's what that looks like here. You can see we're still updating R10. This is Hell's Hall, just one of the indirect system call implementations. So we're updating R10, we're updating EAX, and then instead of making the syscall instruction ourselves, that QAdder in brackets, the malware previously found where a syscall instruction was inside of NTDLL. So now we're jumping in the middle of a function to the syscall instruction, and from the call stack inspection by the EDR, it's going to look like it's inside of NTDLL, and then your EDRs, if they're not aware of this technique at least, will not detect it. So you still have system calls. The EDR is still going to be blind in terms of its NTDLL hooks being activated, and the malware can make whatever system call it wants. But then, as you might suspect, we can detect this very easily with memory forensics. So on the right, what you're seeing is the indirect system call plugin. The process is Hell's Hall, the PID in this particular memory sample, and then we're showing you a disassembly and the addresses where that is. Again, 0 false positives against all of our large data set. So with direct system calls, with indirect system calls, you're not bothering to overwrite the hooks of the EDR. You are just making those calls yourself, but it's still really loud because making random system call invocations is not something you would expect of normal code. If you write normal, clean, reasonable code, you're just going to call the regular APIs that then make the syscall invocation for you. And then with exception handlers and debug registers, this was really fun as well. So back in 2008, there was an article in Frac about writing debug registers, and then we really didn't see it a whole lot in malware, except for maybe some like one-off proof of concepts. But then it came back very quickly in EDR bypasses. The way this works, and you're going to see a lot of examples here in a second, is it gets combined with exception handlers in what's really clever ways. And the idea is by combining abusing exception handlers and abusing debug registers, you can bypass what is most of the EDRs that these researchers found in the wild, that found being used, and then this is what ransomware was doing as well. The basic idea here is we don't want to do what we just talked about, where we're making syscall invocations directly in like a DLL that's not one of the Windows ones. And then secondly, we don't want to have to overwrite the hooked functions either. So we're going to make a syscall invocation, but it's going to be dynamically made, and it's going to be much harder to find. If you're into this topic, reference 40 out of many with this slide deck is like probably a 45-minute read just on this technique. It was super interesting. By the time we read all of that, we basically knew what to do for the plugins, and then we were able to detect this. So this is a project called Mutation Gate. Again, it's an open source version that mimicked what some ransomware out in the wild was doing. And there's a couple functions that have to be set up for this. One is add vectored exception handler. So this is going to make it where that function called exception handler gets called whenever there's an exception in this process. And then what I also have highlighted in red is a function called enable breakpoint, which we'll see here in a second. But as you might guess, it creates a breakpoint. And so this is this enable breakpoint call is going to set a hardware level breakpoint on an address in memory that we want to call. And then after that is a call to set thread context with what's like an invalid context. And so that's going to force an exception to be triggered. So we have our exception handler, we have our breakpoint, and then we're going to force an exception to be thrown. The second function here, kind of halfway down the slide, is that exception handler function. And what it's looking for is what address the exception was thrown for, which, can I go back? Yes. So if you see the second argument to enable breakpoint, we are at this system call of draw plus 8. So the idea is we're looking for if the exception handler throws, we're looking to see if it's the system call that we want to call. So the idea is they pick for NT draw text, which is just like a system call to draw to the screen. No EDR is going to care that you're making that. So the software calls NT draw text. That is going to trigger, when that gets called, that's going to trigger the exception handler path, because that's where we set the breakpoint. And then it's super nice, because what the malware does is dynamically, you can see in the top function set result, What it's going to do is change the system call number. You can see it's updating RAX, which is the same thing as EAX. It's updating that to the system call we actually want to make. So the end result here is the EDR thinks we're calling like NT draw text, and we're calling all the functions that we need for code injection. Okay. So we want to be able to detect these. First, we have to be able to enumerate vectored exception handlers. I looked at this for literally like 1 minute in IDA, and it was horrible. So I just Googled, and there was 2 awesome resources. NCC Group, a big consulting company, had a write-up on how to do this up to Windows 8. And then Dmitry Fornay, another researcher, wrote about it for Windows 10. So we just took what was probably a lot of research effort on their time, converted that to a Volatility 3 plugin and code, and we could enumerate the vectored exception handlers. So that's what we're seeing here. Basically what we do, one thing we realized when we did mass testing of this is legitimate software sets a ton of vectored exception handlers. There's a lot of legitimate reasons to do that. So we do some static analysis. We try to say, does this handler actually look like an EDR bypass and not just any function? The ones that pass our checks, we report them, and you can see here mutation gates being reported because we can, through static analysis, we can tell that its function is trying to do EDR bypasses. And then another version of this is the unfiltered exception handler. Similar idea, it's just a different level of exception handling in a process. But the end goal is the same. This proof of concept also calls set thread context with an invalid address, which is going to trigger the exception. And then we want to be able to find that. Inside the process memory, this was way easier. Each process inside of kernel-based.dll has this global variable, the current top-level filter, so we just go find that variable. We see if the address is set, by default it'll be null. If it's not null, we do our static analysis on that address, and if it looks like an EDR bypass, we report it. So this was a project called EDR-Ception or EDR-Inception that did this way of EDR bypasses, and as you can see, we detect it right away. This is another cool one. So as I mentioned before, there's been this like crazy back and forth of AMSI bypasses. Attackers still want to run their malicious PowerShell. They want their macros to work and so on. So this was actually a super cool use of it. If you're familiar with some of the bypass techniques, what the bypasses do is hook the functions inside of AMSI.dll that actually make the decisions on if a script is malicious or not. So one of the main ones is the AMSI scan buffer. That's what I've highlighted at the top of the slide. So what this project did, it's called patchless AMSI. What it does is it sets a breakpoint on AMSI scan buffer, and then when it goes to run its PowerShell script, Windows is going to try to call that function to say, hey, is this PowerShell script malicious or not? That is going to trigger the breakpoint. So now the malware has control over that decision. And what you're seeing here is an open source thing. What it's going to do is basically just bypass the results. It sets the result to AMSI result clean, which no matter what your PowerShell script is, it's going to say, hey, this is clean, let it run. It's going to adjust the return address and things like that. And then the end result is you get to run all of your malicious PowerShell, and Defender and other EDRs that might be registered are none the wiser, and they don't get to scan it. So obviously we want to be able to detect that. First off, we're detecting the fact that it's based on a vectored exception handler, which we saw before, so we pick up on that. And then we also examine all the debug registers because it really doesn't make sense to use them. And then we use some of the cool new features of Volatility 3. So we not only say like, hey, this process has a debug register set, we figure out the address where that breakpoint is set, figure out the DLL, and then we resolve the symbol name, which you can see is AMSI scan buffer. So there's really no guessing at that point what this malware is trying to do, and we can detect that bypass technique in a couple different ways. So that was the talk. This was a brief version of it. We have a 19-page paper that we published at DEF CON with many more IDA Pro screenshots and all the internals and technical details. And then I think at this point, 5 of the 6 plugins are on Volatility. There's one more we need to like make a little cleaner. But you can start using the plugins as well. And then definitely contact me if you have any questions. And again, thank you for coming to the talk.